when we were getting into Zoom, that was what I always prominently forgot, recording. And then, you know, sometimes 10 minutes into the lecture, you realize it. But at some point, I completely forgot, which meant, but I still had to present a recorded lecture. So right after the lecture, I repeated the lecture to myself, just really talking to the screen, because that was the only solution. Now that's the first thing. I may forget to give the lecture, but I'm not going to forget the recording. This is where we were last time, what you see on the screen. And this was basically the last slide related to my discussion on how solutions depend on their initial conditions. And it just sort of started from this slide here, this question, right? How does the flow map depend on initial conditions, right? And at some point, certainly when I first learned this in an ODE class, it seemed like a very abstract thing because, all right, so you have regularity in the flow map or the solution map, and then let's move on, let's discuss something else. But what I try to convey to you that this is really an essential thing to be aware of, and understanding it in more detail beyond actually even just understanding what you can expect from a bunch of initial conditions, how they evolve. When you start digging around what this implies, the existence of these derivatives, you can get really far, and you can actually end up just getting a very simple tool that you can use to explore a general nonlinear dynamical system, right? So it is worth looking into these rather than just turning, you know, have absolute confidence in numerical methods, which are great because ultimately we're using numerical methods here. But this is a little bit in the spirit of this class, that sometimes less is more, because if you have a fundamental understanding of what's going on with an ODE, then with much less effort, you can get a whole lot more general conclusions that are valid for, you know, more initial conditions and parameters, and that in turn helps you understand what you see or even design new systems and understand behavior. So in the end, we ended up talking about this finite time Lyapunov exponent, which is born out of the smoothness of solutions with respect to initial conditions. And it's a scalar field that you can compute, and features, notably ridges of that field. It also turns out the trenches of that field are equally important for other reasons, but they help you find important structures. They go by the name of coherent structures or Lagrangian coherent structures these days, in actually completely general time-dependent flows, and even the dimensionality can be higher than what I discussed here. And I showed you some examples. First, this was sort of a proof of concept on a two-dimensional flow, and sure enough, it gets you without any prior analysis, which we did here. The prior analysis was we knew the stream function, and the flow was steady. Even in a general 2D flow, the flow is unsteady and the stream function is not given to you. Even if it was given to you, it is not a conserved quantity. So it's not helping you. It's instantaneous level curves, the streamlines, although those are they are thought to be very important in fluid mechanics in visualization. They certainly don't tell you where the material, the actual fluid particle goes. Although in fluid mechanics, people still have a hard time believing that. They teach it in all the classes. That's one of the introductory facts. They teach you that streamlines are different from particle paths in fluid mechanics. But when it comes to their own work, they say, hey, what better tool can you have? I'm still going to plot the instantaneous streamlines, and they should be really close to what the fluid does. Well, guess what? No. If the fluid is very complicated, just highly time dependent, they have very little to do with each other. And you can see that by doing flow visualization experiments, just throwing anything in the fluid, it's not going to follow the streamlines. So then these methods then really become important. I just showed you a 3D example. Even in a steady flow, this is chaotic, and you can explore still the structure. You can see where the FTLE is low. Those are actually vortical regions. And otherwise, this would be pretty hopeless. I showed you also a vortex shedding example. What I didn't go, I just added this, that if you want more of a gentle introduction to these types of methods that deal with coherent structures in time-dependent flows, there's one that I reviewed that I did in 2015, but there's also other reviews that focus more on other. I think this is the most recent review that's available. That's in the annual review of fluid mechanics, but you can apply it to any dynamical system. So I just added the reference here. Was there any further question related to this before I move on? Nothing. The next thing, this is the last fundamental concept that I wanted to talk about in dynamical systems, which again seems like first, always just one of those pedantic mathematical results that you hear about and you can move on, and it's only good for the instructor because they can pose an exam question based on that, right? And if you don't know the answer, we got you, right? And that's what it seems like certainly when I first heard it in an ODE class, right? Okay, so what's the big deal, right? This is just another mathematical statement. I can sleep better even without knowing about it. This is equally important, just as important when you actually work in applied math or engineering, you realize how important that is. So that would actually be not the dependence on initial conditions, but now dependence on parameters. It's the one last sort of general thing, and then I will start discussing actual things that are happening in the phase space of a dynamical system. So dependence on parameters. So the problem, the question is still related to the dynamics of an O. So this is what we're looking at currently, continuous dynamical systems that are modeled by ODEs. But instead of just the usual dependence on x and t, I'm going to add a parameter there. And this is, in fact, a parameter vector, mu. So mu is now a p-dimensional parameter. And x is still taken from some domain in Rn. And I'm just going to assume that f is CR in all its variables. So now it means that it's going to be CR in x, t, and mu jointly. Okay. And I still have an initial value problem. And the existence to this initial, the local existence of solutions is no problem. So based on what we've already seen, there exists a local solution, at least local. And we know that it's smooth in the initial with respect to the initial conditions. But when I write down the solution, now I have to point out its dependence on the initial time because this is an autonomous system. I have to point out dependence on the initial condition. Now I also have to point out the dependence on the parameter because clearly the evolution rule now depends on the parameter as well. And the minute you write it down, that poses the mathematical question that I have just discussed from a mathematical perspective. Well, we know how things depend on t not x naught, right? Because we've just cleared that up. But how do I depend on mu? What's the dependence on mu? And you could say, well, why do I care? I mean, am I not happy just to get a solution for the given mu? Well, no. The reason why we use differential equations to begin with in dynamical systems is not because we are so 100% certain about a particular system. We want to model them and we want to understand them. We want to design them. There's always uncertainty. There's always things we're ignoring. There's always variations, not only in the initial conditions, but also in our model. It's always just an approximation to begin with. And chances are, you're taking the time to write that model down, not because you're so much interested in your own car and nothing else. But when you write down a model for a car, your chances are you're working for a car company, right? Or somebody who consults for a car company. And then you would like to get conclusions over a range of parameters because it's going to influence your design, right? And so therefore, the dependence on parameters is actually one of the most important things that we do as part of our analysis. So as I mentioned before, so the question would be then, and then I get to that question, but let me pose the questions. The question would be, how does the solution x, t naught, x naught, mu depend on mu? And always there's the y, and that's what I'd like to emphasize. I mean, the first thing, y, is the kind of, let me just sum it up in one word, is that we want robustness of our conclusions. About the system behavior under changes, because maybe I'm actually interested in exploring the system behavior over a range of parameters, or uncertainties, because maybe I don't know them for sure, and that's in fact always the case. In the model. And there could practically everything I put in a model as a constant will have its own uncertainty and inaccuracy, right? Whenever I try to get it from real experiments. I mean, when I as benign as me writing down the constant of gravity. I'm going to be doing an approximation. I'm going to write either 10 or 9.81 meters per second. Is that really the constant of gravity? No, it's an approximation. When I put down a density, I'm not going to do super high precision measurements or anything like that. So you get even in the constant that we treat in mechanics is given, they have uncertainties, but those are probably the least of your concern. The other thing is that the other one is there's going to be uncertainties in the measurement. You don't yet know what size of the gadget will be that you're about to design. In fact, they ask you to write down a model precisely because they want the answers from you, right? So there will be inherent uncertainties, plus there will be design uncertainties, open parameters, and so on. But that's not the only reason. There's actually another reason, is that very often we would like to actually, beyond just doing numerics, really, we would like to come up with closed form formulas, kind of rule of thumb design parameters for some features of the behavior, which is next to impossible because this is a nonlinear system. Yet, very often, your system will be close to another nonlinear system about which you actually know a whole lot because it's symmetric, because you've done measurements on that, because you understand that. So that brings you to the idea that maybe if I understand the system well, or a particular feature of the system well for a certain value of the parameter, maybe I can extrapolate that knowledge to nearby values of the parameters. Of course, I can only do that if I have a reasonable dependence. I'm not saying that the behavior should be identical when I change the parameter, but there has to be a reasonable dependence rather than a huge jump in the system behavior with respect to the parameters for me to be able to do that. And that is the whole idea of what generally goes by the name of perturbation theory for dynamical systems, is namely that I know the dynamical system, at least some features of it, for some value of a parameter, and then I like to move that parameter from that location and see whether I can just systematically perhaps work on extending that conclusion. I don't expect the conclusion to be the same, but systematically work on extending it. So the other reason would be perturbation theory. Which would be, well, what's perturbation theory? So analyzing system for mu minus mu naught much less than 1 based on knowledge at mu equals mu naught, right? So you somehow know things about the system and mu equals mu naught, you then know some solution. Can you extend that? So there's plenty. I mean, one of the most, say, mechanics, but this is fundamentally a course related to mechanical engineering or engineering. One fundamentally that where that comes in is weakly nonlinear oscillations. That's what we call them. So you have a nonlinear dynamical system which tends to oscillate, but it's close to a system that is in fact linear. So the generic form of such a system would be, just to simplify, to say, so in 1 degree of freedom, it would be some mass times some displacement double dot, then you would have some damping, linear damping, kx dot plus cx. So this is, if you learn mechanics, then you probably, some call this the MKC system, except that you may have matrices here when it's multidimensional. That's also covered by this. And that's a linear system for which we pretty much have a complete theory. We know how to solve them. And the only challenge maybe is some huge dimensionality. Then when you compute the appropriate eigenvalues, eigenvectors for the solution, then that can be a challenge when it's in the order of millions, right? But at least even then we have an algorithmic procedure for that, right? We have formulas, and it's just all about evaluating those formulas in a smart fashion. But all bets are off when you start adding nonlinearities. But what if the nonlinearities are small? So everything I'm adding here is such that epsilon in norm is much less than 1. So in that case, when I pose the problem like this, then then I would say that mu is just epsilon, right? And it's just is the element of R1. So in this case, the dimension of the parameter that I'm interested in 1, and the critical value around which I'd like to perturb and extend my knowledge to the non-critical values would be epsilon not equals mu not equals 0, right? Because in that limit, I only have a linear system that I know well. Can I use the solutions of that linear system to extend my conclusions about the linear system for epsilon small? And that immediately means that I don't mean extend. By extending, I don't mean, when I do perturbation theory, is to try to use the same type of solutions to solve this nonlinear system, but somehow start building on those solutions to construct solutions of this system, which generally cannot be solved. The only case in which we know how to solve this is when this is either linear and there's no dependence on x dot and t, or maybe there's dependence but linear, then we simply then add modifications to these two. But if this is truly nonlinear, then we don't know how to solve. I mean, again, another case that we know how to solve is when it's just purely forcing, independent of x and x dot, because then it's just an inhomogeneous linear system, right? So what do we do? Well, when we look at weakly nonlinear oscillations, then we basically follow the usual approach. Which would be perturbing off. So expand near null solution. Expand in epsilon near linear solutions, which is null. So we basically assume that, or a lot of people, let's assume that x epsilon of t, which is a solution of this, is some solution of the linear problem plus epsilon times f1t, phi1t, sorry, plus epsilon squared times f2t plus blah, blah, blah. And high order terms, in fact, I can write the blah, blah, blah. And this is what you would find in a lot of even applied math texts, but certainly in engineering, articles, and so they would present this as an ansatz, right? Now, wouldn't it be nice to know, though, whether this ansatz is justified? Can you really write the solution in this fashion, rather than just assuming that you can write the solution? Do you know for sure? Do you know when this is not the case? So this is what the fundamental theorems bodies are for. Because make no mistake, when you write something like that, if this were to be true, then you're essentially saying that this derivative, you're expanding the solution with respect to mu. So this would then be the derivative of x epsilon with respect to epsilon at epsilon equals 0. And that derivative must then exist. If that derivative doesn't exist, if your solution therefore is not smooth in epsilon, or more broadly, coming back here, if this solution is not once continuously differentiable in mu, then this ansatz is not justified, right? And likewise, when you go for high order terms, what you see here, this phi2 in these guys, if this is really true, then this should really be the second term in the Taylor expansion. So this should be the second derivative of x epsilon with respect to epsilon at epsilon equals 0. Okay, so do these exist? Is it worth though spending time on this? Because you might think, I mean, real life is not necessarily like that, because in fact, very often, when to turn this into anything mathematical, we have to assume that epsilon is in fact arbitrarily small. It's very, very small, tiny. And you might argue that, hey, that's just again a mathematical question. In real life, who's going to have tiny perturbation? We're going to have substantial nonlinearities. But amazingly, a lot of the problems are of this form. I mean, most notably, what comes to mind, I was just thinking before class, I mean, what would be the simplest example? And the simplest example, just I thought back to the times when I was in the military, which I was. I had to be for a year. And one of the first things you learn as a soldier, discipline, you keep stride. So you don't just, when you walk outside the camp or inside the camp and you move in formation, you're just going to walk around and, and look around how interesting other people are and so on. You keep pace, you keep stride. However, The minute you reach a bridge, automatically, the officer doesn't even have to tell you, you break stride. That's the rule. So why is that the case? Well, it turns out all armies in the world are taught. So why is that? Because it doesn't seem like, I mean, all right, certainly my footfall, just one, is not going to do anything to that bridge. It's tiny. Now you take 15 of us, I don't think so. The kinds of forces we are exerting are absolutely negligible. The bridge, when you take all the stiffness and the mass of the bridge, they're still tiny. And yet, I think it was in 1831, something I just looked it up quickly, if I remember correctly, when this first time happened in England, that a group of soldiers were marching through a bridge and they managed to destroy it by keeping stride. So if you hit the right frequency, even though the actual forcing, the impact on the bridge is tiny, it's absolutely tiny, right? If you hit the right frequency, right, and then you can actually destroy a bridge, right? And then you would think that people have learned from that. Well, armies have certainly learned from that. But then I read somewhere that I think it was 2005 or no, it was actually 2000, I believe, that there was again, out of all places in England, in London, the Millennium Bridge, which was a super advanced design. And on the opening days, on the opening day, a large number of people were flocking there, right? And they managed to cause large oscillations in this very modern, robustly designed bridge. And why? Because, of course, people will keep stride. Well, that's an interesting thing. So people, why would people keep stride? Nobody tells them, right? So why would a group of random people will keep stride? Well, there's this thing which is called synchronization. So after maybe a group of people starts being near in step with each other, and they start detect, and also they are moving in a crowd, there's a natural tendency in dynamical systems in individuals that have some sort of coupling between them, among them, which is, well, you basically have to fall in line. It's a huge crowd, right? So you cannot just arbitrarily step, but there will be sort of nearby people will naturally synchronize. And then if in addition to that, that starts a little bit of vibration for the bridge, then they also, in addition to that, naturally synchronize with that, even unknowingly. And that really that did lead to sizable oscillations on this modern bridge. And people, the engineers assured everybody that it would never have been a catastrophe, yet they closed the bridge for a year just to do additional work on that. So anyway, that's just long story short, that even that tiny additions to a model, even though they're really tiny compared to the original model, can make a major difference. And in fact, in many cases, that's exactly what you want to find out, like in a bridge like that, right? And then people were unprepared for that when they were designing it. So that epsilon much less than 0 is actually very, very relevant in a lot of systems, right? Because the ballpark design is already okay, but you had all the damping in the world that you want in your car window is not going to be shaken by some violent force from the engine because you made sure that any interaction between the two is damped. And yet, as your car grows older, at certain frequencies, at certain RPMs, various parts in the car will start vibrating. Why is that? Is the engine really shaking it directly with a large amplitude? No. There's a conduit between them, chain of interactions, which are tiny, right? But at some point, that tiny interaction still hits the right frequency and then causes a large vibration. So that's why this is a very popular subject. And that's why we need to understand whether this is justified or not. That's why I put a question mark there. So the good news is that we don't have to do much work. So it turns out that the regularity in mu, which is differentiability, is just a short term for that, turns out to follow from things that we've already seen. In X naught, which is surprising, right? So how would this parameter here is of my own making, which is a change to the model, whereas this is the initial condition. I listed the two as completely independent of each other. So how would a result that I have for x naught imply a similar result for mu? They play very different roles, right? So this is a good opportunity for me to introduce one of those dirty tricks in dynamical systems that just by a formal trick, you actually immediately get the result without working too much. So how do you do that? So the trick to make this inference is the following, that you rewrite the equation x dot equals f x t mu, and I have not done anything, but now I'm adding a dummy equation, mu dot equals 0. Of course, mu dot is 0 because mu is a parameter. So this is sort of what people refer to sometimes as dummy variable. So you view a constant, which you know doesn't change, as a variable. Okay, so what does that buy for me? Well, then I continue writing the initial value problem, which is x at t naught equals x naught. And you know what? I'm going to be even more dummy, because I'm actually not only saying that it's not changing, but I'm actually explicitly adding that as a requirement that mu should be the exact same mu naught what it was at time equals t naught, right? So this is an extended initial value problem, which restates the obvious, but it's certainly not incorrect. It just feels dummy, right? But then comes the trick, is that let's introduce a new variable, which is capital X, which will be my original variable plus the dummy variable. So this is now taken from Rm plus P. Okay, and let's introduce a right-hand side, a large right-hand side, which will be f, whatever I had before, and then I add 0 to that. Okay, so that's going to be my dummy right-hand side, and that dummy right-hand side, the large one, is actually dependent. I can view it as something that depends on that capital X, right? Because it depends on x and depends on mu. Also depends on time, sorry. Okay, so then I can rewrite the initial value problem, the dummy one, as capital X dot equals f of xt and capital X at t naught. I'm just now restating the initial conditions here, equals x naught mu naught, right? Which I call capital X naught. Now, why did this help me? This is a new initial value problem to which if f was CR, which I didn't state here, but somewhere I stated that. I stated that at the beginning, right? Well, f was as nicely differentiable as I wanted it to be, say CR times in all arguments. What I have added here is certainly as many times differentiable as you want it to be, right? Because it's just dead 0, right? So that's certainly that the addition of that component doesn't change the smoothness of the right-hand side. So you then have f, this capital F, being CR in all its variables, which I just summarize as capital X, right? Which now includes x and mu as well. Therefore, the corresponding flow map or solution map has that dependence that I want. So based on what I have here, by earlier result, I have smoothness of the solution, the large extended solution, with respect to its initial conditions. Okay, but if that solution, which includes x of t and mu of t, is CR in its initial conditions, then each of its components is CR in its initial conditions. In particular, the first component is CR in the initial conditions. But what is the initial condition? Well, the initial condition has two components, x naught and mu naught. Okay. So therefore, this full solution, as well as its one component, not only is it CR in the initial condition, but also in the parameter. If I I change the parameter, it will have the same CR time dependence. So it follows that X, T naught, X naught, X naught, mu naught, and I can write now mu naught, which is the same as mu because it doesn't change. But if I think of it as something that can change, which is the same as when I think of the initial condition as something that can change, then it's CR in all variables, right? So it has come out just as a gift based on the earlier result, whose proof I didn't do, but I referred to Arnold, right? So again, when by inspection, this is important to know, if you have a dynamical system, whatever dependence you see, whatever smoothness you see for all variables here, the solution will inherit that as well with respect to the same parameters. So therefore, when I skip back here, if this was really only the dependence you had here in epsilon, okay, then the right-hand side, well, you have to write this equation in a first-order form. So you would like, you know, x1 dot equals x2, and then you would write x2 dot equals 1 over m times everything you see here. But that doesn't change the fact that the right-hand side, which would be x2, which is x dot plus whatever you see here, is as smooth in epsilon as you want it to be because it's linear. So if this was really the case, then this is no longer just an assumption. This is a completely legitimate way of writing the solution because the solution is C infinity in epsilon. You can keep going, okay? In practice, however, what I've written is a bit of an oversimplification because there will be additional dependence here on epsilon inside that function, right? So not only is it small by some parameter, but also there can be inside dependence here. Then I have to modify what I have said because this internal dependence on epsilon must be smooth as well. So I need to look at the function as a whole if it's CR, but if it's CR, then this is okay, right? So then for weakly nonlinear oscillations, if epsilon times f x dot epsilon and even t is CR in epsilon, then x epsilon t can be Taylor expanded indeed. Up to that order. So it's not an assumption, it's a given, it's a fact. But it also means that if you have some funny parameter here coming from non-smooth interactions, impacts, whatnot, then you cannot write this. There's no a priori justification. You have to think of other approaches. For non-smooth dynamical systems, non-smooth with respect to a parameter, that's what I mean here, then this ANSA, you have actually no reason to expect this to be the case. So let's see how, any questions on this, how this would help you in an example, because that's one of the fundamental tools of dynamical systems to do perturbation theory. So if you haven't done it before, or can we put it in the framework of dynamical systems? If you did it before, let's consider an example. But I stop for a second if there's any comments or questions. The one that I picked in my notes is a simple calculation, but in order to give you a flavor, it gives you a flavor. This would be periodic oscillations of a nonlinear. Let's go with the springboard. It's like a beam, but it will be an OD model for a beam. So the story is like this, that you have a beam which is fixed into some foundation here, and that has some curvature here. So I'm actually now spending some time a little bit on modeling how the local circumstances that, you know, I have this elastic object that's sticking out of here. And like I said, there's some curvature here in the wall. It's just how you know, because you're not going to have an exact fit ever. That's just an idealization. So this is the little deviation from an ideal situation, which you could consider as linear as long as the amplitudes are small. So if I had this, you could really consider this for small amplitudes if it's perfectly elastic as a linear vibration in this direction, you know, undamped linear vibration. Okay, and you could even measure the displacements in this direction. Okay, but I'd like to make a first order correction and see how this influences my vibrations. This little arch here. So effectively, what you can think about, you can imagine, is that if I start displacing this beam and it starts touching this arch here, this radius, so the effective length of the beam, which is freely oscillating, has become shorter. If it has become shorter, that means that it's effectively a stiffer beam, right, in both directions. So if I now look at the spring force and I want a more accurate model for the spring force, not just linear, then, so this would be F spring, and this is, say, X. Then what starts out to be linear will start, so near the origin, it would be just linear, but then it starts hardening in both directions. It's the classic case of a hardening spring. And the hardening effect is because the effective, when you increase X, the effective free length of the beam decreases. Okay, so it basically is stiffer beam or hardening beam. We model it by a hardening spring. Still model it as a one degree of freedom problem. So the one will be the model for this 1 degree of freedom model will be X double dot. Just for simplicity, I'm not using any parameters. Normally you would have here the mass, but I assume just everything has been non-dimensionalized. And in first approximation, this will be super weakly damped anyway. If this is a perfectly linear structure, it would take a long time for this to die out. And I just want to roughly understand kind of the short-term behavior. Therefore, for a while, I ignore the damping. So this is essentially a linear oscillator at this point. But what I don't want to ignore is the fact that I have a hardening spring here, right? And I have put the epsilon there because this effect is still tiny. So when I really want to work out what's happening here, then that will be tiny. So that means that the spring force will be X, again, after non-dimensionalization, plus epsilon times X cubed. So this is a fairly mild effect. Nevertheless, it does make the system nonlinear. And I have, whereas I know how to solve this one, can I extend my conclusions to this one? Can I predict the types of vibrations that this beam will have? Okay. Or the springboard. So I still have, then corresponding to that, I have an initial value problem. So at T naught, what did I pick here? Suppose I really just apply a displacement here, push it down with 0 velocity and then let it go. So I'm defining an initial value problem, which is like this. Why am I specifying 2 values? Because remember that for everything we do in dynamical systems, we use theorems that are fundamentally stated for this system. First order systems. This is a second order system. So you always have to then think about the fact that you're rewriting this as x1 dot equals x2, x2 dot equals, in this case, minus x1 minus epsilon x1 cubed, right? And then this is now a 2-dimensional dynamical system, so you need 2D initial conditions. Or you just remember your first ODE class in which you were told that if you have a second order ODE, then you need 2 initial conditions. Okay, but the dynamical system's view is that all ODEs are first order ODEs in an appropriately enlarged phase space. So the reason why we like that, because all our theorems, all our results are for that one. And it also carries the geometric flavor that what we favor these days, right? Now, when you do that, right, then this will be the only nonlinear term on the right-hand side. This is as smooth in everything as you want. Smooth in epsilon, smooth in x, so you will not have no problem with the initial value problem. So the right-hand side of, let me write it down, x1 dot equals x2 dot equals minus x minus x1 cubed. So the right-hand side of is CR in all variables, okay, for all r bigger than or equal to 0. So the solution, or the flow map, is also CR in not only the initial condition, we knew that, but also in epsilon. So it's okay for me to seek an expansion. So this is not an ansatz, but this is a legitimate expansion in which you start with a 0th order term. And in that case, this will be the solution of the linear problem, right? Which you know, plus epsilon times phi 1t plus epsilon squared phi 2t plus higher order terms. And I can really go as long as I want, and I can increase the precision of this approximation, no problem, right? What do I know about phi naught t? Well, phi naught t would be a solution of the linear system, and I have some freedom here as to how I pick that, because there are lots of solutions to the linear system, okay? Infinitely many. Now you could say, yeah, but I happen to have an initial value problem here, to which I will say, you're absolutely right. I happen to have an initial value problem, but for the full solution, not for the solution of the linear system, okay? However, this, I have uniformly stated this in epsilon, irrespective of epsilon. So it must hold this initial condition for each value of epsilon. Among other things, it must hold for epsilon equals 0, because I never said that it's only hold for epsilon. I left the epsilon open but small. So it must hold also when all these are out. So that therefore the best choice is always when to set the initial condition, to enforce the initial condition already here. And I will construct the rest, that these will automatically just add 0, both to the position and both to the velocity. And therefore, irrespective of epsilon, the initial condition is always satisfied. So these will always be selected in a way that they satisfy trivial initial conditions, namely the sum of their positions at time equals 0, t naught is 0, and the sum of the velocity is 0, okay? So this must satisfy the initial value problem for epsilon equals 0. So then essentially you're looking at this equal to 0, right? And to that, since I have to assume that you've seen all these before, the solution to that is phi naught t equals the amplitude a naught. Now, normally I would have sines and cosines, but I have no damping, so I can just write down with confidence that this is cosine t. And I didn't have any frequencies here, a times cosine t. That's the solution. You plug it in and you find that that's the solution, right? So basically, the cosine function is the property that's a naught at 0, and then it starts oscillating, okay? And this is then the idea of perturbation theory, that I know that one, and what can I say, you know, what sort of correction can I come up with so that I get a reasonable approximation to the nonlinear solution? Well, I need to know what I'm looking for, because if I just leave it completely open, and I'm not going to get too far, it turns out, because also this system has many solutions, and many of them at this point, you know, many of them I can launch them from the same initial condition, which is identically 0 for these, but what are the ones that I'm really interested in? So a common feature of perturbation theory is that you have to have some idea about what you're looking for. Now, from the physics of the problem, this is a conservative system, doesn't have any damping. So if I pull it down and starts oscillating, I expect vibrations. There's no damping, they're not going to die out. So what I'm fishing for is periodic vibrations. So I look specifically for periodic oscillations. So what are they like? Well, I will write that these high order terms, the FITs that I'm looking for, are all periodic. So when I add an appropriately chosen period, T, it cannot be a TI, right? Because if I pick various different periods for these, all of them, then the end result will not be periodic. Now it can be a now this is already has a period, okay? But at what I'm really asking at this point, that the reason why I'm leaving this open, because if this has period 2 pi, okay, maybe it's okay to have something here which has period pi, because after a while that will be also periodic, right? If something is already repeating with period pi, then it's also repeating at 2 pi, so it's not going to set up my assumption. But for the same reason, the period might be 3 pi or 5 pi, and it's still okay. So there's even though I want the whole thing to be 2 pi periodic, but these can be sort of faster oscillations as long as they have a common period. That's why I'm saying that I don't know exactly what this is. I already have constraints on it. It cannot be some sort of irrational, it cannot have an irrational relationship to the period of this one, but fundamentally, I don't want to push enforcing it. Now I want to leave that open. So T is the period to be determined. What I know for sure is that some integer multiple of this T must be equal to my current period, which is 2 pi. Because otherwise the full solution would not be periodic. Okay, so that's the only thing I'm going to assume. And then I take this. At this point, this is an ansatz. This is an ansatz because mathematically, I don't know yet for sure whether, unless I have a very advanced result that I'm not using here, that this system will have oscillations like that. So this was not an ansatz. This is an ansatz because this is what I'm fishing for. I either get such a solution or not. There might be other reasons that I'm not using here that guarantee such a solution, but based on what we have, the fundamental results, this is an ansatz. Okay. Let's see if it works out. It seems like physically it's justified, right? I do expect periodic orbits, so let's just see that. So substitute star into this, let's call it 0, because there's a 0th equation that I'm looking for. So I have two things to substitute. This is not right to say because it's not the answers. I'm substituting the solution. Let's call this star. Sorry, let's call this double star. So a substitute star into 0 and use the ansatz double star. So star is a fact. The second one is an ansatz. So let's first do the substitution, substitute the fact, which means that I need to take this expansion, plug it into this ODE. The initial value problem is still there, and then I'm going to use the ansatz. So when I plug it into the ODE, then I take the expansion and plug it into the second order term. That's just a linear operation, taking the two derivatives, phi 0 double dot plus epsilon times phi plus blah, blah, blah. And then I had the second term here, which is just x itself. So I'm just going to take this solution, plug it in there. And the third term will be epsilon times the solution cubed. So that's what I'm doing, plus epsilon times, no, sorry, first the solution itself, phi naught plus epsilon phi 1 plus blah, blah, blah. I'm not writing out the higher order terms. That was a double dot here, because I hope I can get away with just featuring the lower order terms at this point, plus epsilon times phi 0 plus epsilon times phi 1 plus blah, 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 cubed equals 0. So that would be certainly the case. And this must hold for at least for small epsilon. So I have all sorts of, I essentially have a Taylor, an expansion in terms of epsilon, a combined expansion on the right-hand side, on the left-hand side, and I have identically 0 on the left-hand side. So this must then hold for all times because phi naught is a function of t, and also must also hold for epsilon. So again, I have a function of epsilon and t on the left-hand side, and I have a function which is identically 0 on the right-hand side. So whatever I have on the left-hand side must be identically 0 as well. So when I view this as a Taylor expansion with time-dependent coefficients, which it is, right, then each and every coefficient must vanish in the Taylor expansion because this must hold for any value of epsilon. And yeah, if I have a Taylor expansion with respect to epsilon with those coefficients, then the only way it can be identically 0 for arbitrary small values of epsilon. I can't keep epsilon equal to 0 because then I just keep looking at the linear problem. So the only way I can be identically 0 is that all those coefficients in the epsilon expansion, those time-dependent coefficients must be identically 0, right? So that's when we say, so must hold for all epsilon small. So orders of epsilon must have, or powers, I should say, must have identically 0 coefficients. I mean, if you've done this before, I'm sure you have, then people would say, well, let's compare powers of epsilon. The only reason I'm spending so much time on it, because let's just look at it, why that is justified to do, because we like to be as precise as possible. So what are the 0th order powers of epsilon, or the order 1 terms in epsilon? There's one here, there's one there, and everything is order epsilon there. So the first one gives you phi naught double dot t, and mind you, that's a function of t plus phi naught equals 0. So basically at order 1, you have recovered the linear oscillator. And that's a good thing because that's exactly how we constructed phi naught. We wanted phi naught to be a solution of that problem. So far that checks out. It also solves the initial value problem. But the reason why, but I knew that, right? So that's no surprise because that's how I built my solution. The real question is these terms. So now I go and then look at the order epsilon terms first. So I have one here, right? I have one there. And when I start working this out, then I don't have to work too much to get the order epsilon terms because this will be the epsilon times phi naught cubed, right? From this one. So if I collect those, then I get phi 1 double dot plus phi 1 plus epsilon times phi naught cubed equals 0. And it's really good that this is not a nonlinear equation because the variable in this equation, the unknown, is phi 1, and phi naught is already known. So this is a time-dependent function. So it's basically a forcing on a linear equation. So just to emphasize that I actually rewrite it as phi 1 double dot t, which I don't know yet, plus phi 1 t equals minus epsilon phi naught cube. And I know what phi naught cube is because we have already solved for that. So remember, phi naught of t was a naught times cosine t. So this is just minus epsilon times a naught cubed cosine cubed t. I used to know these identities, but now it's easier if I look it up. This is minus epsilon times a naught cubed. And there's this relationship that you can write this as a sum of linear trigonometric functions. So that will be 1/4 times cosine 3t plus 3/4 times cosine t. I learned these back then in high school as linearizing formulas, and I knew them probably up to 4th order. And But now I would know how to derive them, but I don't remember them anymore because I use them on a daily level. So what am I getting here? What I'm getting here is I have a linear spring, a linear oscillator, and on that I have this external forcing. Okay, can I solve this equation? Yes, that's again in the basic ODE class. You learn various methods for solving this equation. Perhaps the simplest one, and that's that I'm going to use, that requires the least bit of knowledge, is the method of trial functions, right? And basically, you know that the solution that I think I denoted by phi1 of t without any special notation will be the solution, the homogeneous solution to the homogeneous part, which is the unforced part of this linear differential equation, right? Plus the inhomogeneous. That's a property, which is a particular solution. Let me call it that way. Sorry, that's not a particular solution. Okay, plus the homogeneous part, and then you already use the homogeneous part to satisfy the initial condition. What will be the initial conditions that we want for phi1? Well, generally speaking, what we want for phi1 is that it should be 0 at 0, and we also want that phi1 dot should be 0 at 0. Reason again is that I've already used phi naught to satisfy all the physical initial conditions that I had at the beginning. The leading order term is already satisfying that independent of epsilon. So then everything else, since it must hold for any epsilon, it can only hold that all these are 0 at time equals 0. Okay, so that's what I have added there. So this method of trial functions would be then is that you kind of try to build a particular solution. So the homogeneous solution, that's what we learn. It's always the same. We don't have to guess that. And that homogeneous solution to this equation is always just the sum of sines and cosines, right? So the general solution to this with frequency 1, because here I don't have a general omega, but I have 1. So if I start writing this out, and first writing the homogeneous solution, which would be some capital A times cosine t plus capital B times sine t. So that would be the homogeneous solution. And then I start adding the inhomogeneous solution. And then we learn for basic, in a basic ODE class, just kind of look for those by inspection. There are other methods, but again, the simplest one is that you say, all right, so I take some particular solution to this whole equation, and it has to be such that if I take its second derivative, and then I take and I add the function itself, then the linear combination of these two should take care of this term here. And I can address that, canceling that term out separately because it's a linear equation. So I can feature various terms in my trial functions whose objective is that once I have differentiated them twice and added to themselves, then they first cancel out this term. Then I have another bunch of trial functions that after differentiation twice and addition cancel out the other term. That's just the beauty of linear systems. So that motivates your choice of then say, okay, so how can I cancel out cosine 3t? Well, I should pick in this case because there's no other term. If you had a phi dot here, then it would create sine 3t's as well, but you don't have a phi dot. If you actually start with a cosine 3t, it gives you something times cosine 3t, and then that's also cosine 3t. So chances are that if you then properly pick that constant, whatever multiplies cosine 3t, then you can knock this one out. So that motivates that you, with that c to be determined, you include cosine 3t as a trial function. Now the same logic would normally work as well, that how can I knock out cosine t in this equation? How can I get a cancellation? Well, again, second derivative of cosine t is cosine something times cosine t. And this is also cosine t and cosine t. So why don't I take on as cosine t as the next term here, some d times cosine t. that normally would work, but there's a slight problem for that. The reason why it worked so easily in this case for cosine 3t is that there was no resonance here. Because the minute there's a resonance, which means that the frequency of the forcing is the same as this frequency here, which is currently 1, then by adding cosine t here, you're not getting an independent solution from these. And this part, so you're basically just, you could just subsume it there. Okay. So when we have a resonance, this is resonant forcing. Okay. And it's a resonant forcing because if in this equation, you know, normally having, you know, some sort of omega 1 squared, which is identically equal to 1. It forces with the same frequency, the same equation. So this is resonant forcing. And what we learn in ODEs in that case, okay, that's not the end of the world. But the way to get that independent solutions, only in that case, not in other cases, that you have to introduce a time-dependent, linearly time-dependent amplitude. And then you really have to potentially have sines and cosines. And that would be E times T sine T. And that really comes because of the resonance. It's interesting how resonance arises, right? Because nobody's forcing this beam from the outside. This is an autonomous differential equation. Nobody's forcing it from the outside. Yet when you start constructing nonlinear solutions, as a byproduct, you will have to solve now time-dependent equations to move forward, right? And then a resonance arises. And then you have to include this no matter what, okay? Which we still, you know, that, okay, then you said, all right, I'll just, you know, use the appropriate initial conditions and then find these coefficients, which is what we do in a regular ODE class. And that is absolutely fine. You could do that. You could, this differential equation certainly has, even under resonant forcing, a solution. That's not the end of the world, right? It tells you that it's growing, right? But it's not blowing up or anything. This is the form of the solution. And you simply just have to make sure that this term vanishes at t equals 0, which it does already automatically. Well, this one doesn't, right? So you get equations for C, D, and E from those. Are we done? Unfortunately not, because so far I have ignored the ansatz. And the ansatz says that I'm looking for solutions, which are also the physically expected solutions, that are periodic. And this is by no means periodic. You absolutely have to have the resonant response there, because this is an essential thing that happens when you force this oscillator with the same frequency. And this leads to growing oscillations, linearly growing oscillations. So that means that phi1 of t is not periodic. If it's not periodic, we have a problem. So we violate the ansatz because we required all these terms to be periodic for the end result to be periodic. So ansatz is periodic ansatz. Cannot be satisfied. So I have failed to construct this solution. Well, if I'm very confident in my abilities, I could just say, done. That means that the original system doesn't have a periodic solution. But then, you know, somebody would say, well, wait a second. I mean, the physics says otherwise, right? I mean, why would this be not periodic? And okay, assume that it doesn't have a periodic. So just assume for a second that you're right. You're coming back to me with this solution, which has growing amplitudes. But that cannot be, because this system, maybe I wasn't smart enough to include the damping, but I certainly know that it's not being forced. So how could it have constantly growing amplitudes, which means that its energy is slowly but steadily going to infinity? That violates the conservation of energy. There's no way that this can be right. And indeed, it's not right. So what's wrong here? Because we have a fundamental result that the right-hand side is CR in epsilon. That cannot be wrong, right? So what is the extra piece? Where am I making the mistake here? because I'm also not wrong in assuming that the solution is periodic, right? Because that's what the physical assumption is. So this is a good example that one really has to scrutinize one's own assumptions and make sure that what I have in mind is really what I'm saying. You know, very often there's the saying that the problem with computers is that they don't do what you want them to do, but they do what you tell them to do. Exactly, right? It's a little bit the same here. You want a periodic solution, and that the procedure will then not give you what you want, but what you actually tell them. And maybe what you actually tell them is different from what you want, and the answer will be given to what you actually tell them. So what is this thing? Let's just scrutinize this ansatz, because everything else is pretty much unquestionable. What is it here? I mean, I'm looking for a periodic orbit. Where am I being wrong? Well, one thing that I'm actually being unreasonable about here is that I'm looking for a t, which for all purposes I'm treating as a constant. And why would the period be independent of epsilon? Because that's what I'm saying. This is a constant, and this equation has a dependence on epsilon and dependence on the degree of the strength of the spring. And I have essentially said, never mind how strong that spring is. I'm just looking for some fixed period. Okay. And if you keep changing epsilon, the strength of the spring, that period will remain the same. This is clearly unreasonable, right? So you bought it because that's the way I presented it. Okay. But the reason I'm going through like this, I didn't make, I'm making a huge assumption here that the t is independent of epsilon, because I wanted to show you how easily we all the time realize that what we write out is actually a whole lot more stringent than what we originally had in mind. Okay, because now I think about it, I have no problem, you know, with that period, which depends on epsilon. In fact, that's reasonable, but that's not what I wrote. Okay, I wrote that this is constant. So the resolution of this would be the period t should actually depend on epsilon, or should be allowed epsilon. Okay, and I don't want to redo the calculation now. So again, what I'll do, I'll just walk you through my notes. Okay, that's so instead of again writing everything in detail to see where that makes a difference. So first of all, I'm going to switch now, and then I append these to the regular notes as I did last time, because I'm a little bit behind in terms of what I wanted to cover. This is so D should depend in epsilon. It says my notes, and this is an actual numerical simulation of the beam for various values of the spring for epsilon. So when epsilon is 0.1, then you get this curve, the red one. When epsilon is 1, you get the blue one. See, clearly, even though they started from the same initial condition, they very soon start shifting from each other, and the phase difference grows. That does clearly signal that even though they are both periodic signals, they have different periods. So clearly there is a dependence on epsilon, as we actually would anticipate. But the way we have set the problem up, we assume that this is not the case, and in fact made the problem unphysical, and the math resists that unphysical assumption, luckily. So then how do we go about it? So this was actually an idea that goes back to Lindstedt, I think, well, at least a century ago. I think so, probably a bit more, and where the community was facing these problems. And then his idea was, okay, epsilon, we have smooth dependence on epsilon, but let's just try to rewrite this series in a smarter way. And he says, even at order, let's just reorder those terms in the expansion and to begin with. So even my phi naught is allowed to depend on epsilon, but its overall magnitude is still order 1, right? So even this term, I can still consider it at order 1 technically, if I wish to, because order 1 means that even if I divide it by epsilon, it has, no, order 1 doesn't mean that. Little o1 would mean that. So big O1 just means that the leading order term there is independent of epsilon, but it doesn't mean that there are no other terms there. So this is just a regrouping of that expansion. I don't know yet how exactly I'm going to do that, but I allow for that. And similarly, I allow phi1 to depend on epsilon as well. I allow phi2 to depend on epsilon. And this is no violation of what I already know, because if all these functions are also individually smooth in epsilon, then this is just another way of writing smooth dependence on epsilon. Okay, it's basically this rearrangement, grouping together certain terms and going for them simultaneously is what actually turns out to help in this case. This is a trick due to Lindstedt, but also more importantly, let's account for equally importantly, let's account for the physics. So these phi i's now, the reason I made them dependent on epsilon was in fact because this is the reason why, although this may look funny. I wanted to say somehow that the periods of these phi i's where they are all the same, but that period depends on epsilon. And the only way, therefore, for this phi I to have an epsilon dependent period is that itself must depend on epsilon, right? If a periodic function has a period which depends on epsilon, then that is just to say that the function itself depends on epsilon, right? So it's no longer correct for me to say that this is order 1 independent of epsilon, right? So the two go hand in hand, and the only reason why I've done that, following Lindstedt's idea, is to allow for an epsilon dependent period, because there's every indication that that's the case. So when I write the dependence of phi I being non-trivial on epsilon, what I really mean mostly, although I do allow for additional dependence, is this one, that the period will depend on epsilon, okay? Then there's another trick, operational trick, which is supposed to help the calculation, because this is now a really kind of embedded dependence, the period dependence on epsilon, and it's a bit harder to work with because it's not at the level of the equation, right? If I just plug this one in, there's a lot of hidden dependencies here. So to bring that out, this trick is I believe also due to Lindstedt, is first, you then rewrite the period as 2 pi over angular frequency, which is always true for any period. So this will be then the frequency of the oscillation that I'm looking for, but that also depends on epsilon. And it is then this omega epsilon, because its dependence is smooth, everything is here smooth in epsilon, that's what the main result was buying for us. I can now go ahead and Taylor expand the frequency along the linear frequency. So at this point, not only am I expanding the solution in epsilon, strictly speaking, I'm not even expanding the solution now in epsilon, but rewriting it as an epsilon independent combination of other solutions. But I'm expanding the period in terms of epsilon. So this is the linear period 1 plus an order epsilon correction. There's an order epsilon squared correction and high order terms. And this is still embedded because it's in the period, right? So it's somehow inside the dependence of phi, the dependence on time. And one way to bring that out, to make it work so that our algebra is easier, is the last trick in this. There's maybe 1, 2, 3 tricks. And I mean, people have tried their luck, and there have been methods that worked better than others. And this is a good operational method to rescale time, because then I actually you'll see in a second that this dependence will no longer be carried in the argument of phi. The argument of phi will be in the new time free from any epsilon dependence, but it will be carried externally by the equation itself. So it will be easier to work with. So when you rescale time, you introduce the new time tau, which is this omega epsilon dependence omega frequency times t. The reason why we introduce new times, then we want to express the ODE with respect to the new times. So you need to be able to say how the derivative with respect to tau is related to the derivative with respect to t. And by the chain rule, if you want to, this is what we currently have in the equation. I want to express that as a derivative with respect to tau. We have, second derivatives with respect to t, first derivatives. If I know how to take a first derivative, then I can also, from that, I just do that twice. So a first derivative in t by the chain rule is the same as taking a first derivative with respect to tau, but by the chain rule, I have to then take the d tau dt, right? And the two are then equal. So whenever I take the derivative of something with respect to t, then I can take the derivative of that with respect to tau, but then I have to multiply it by the derivative of tau with respect to t, okay? The derivative of tau with respect to t, since it's a linear relationship, just omega over epsilon. So d by dt is omega epsilon times d by d tau. So if I want to express d by d tau, then this is 1 over omega epsilon d by dt. But what I do operationally in the equation is that whenever I see d by dt, I just write omega epsilon times d by d tau. And if I need to take two derivatives, then this factor will enter squared. So that's why in the new time, where x is just dependent on tau, and I'm not gonna then, I just view tau as an independent variable anymore. There's no funny business on the internal dependence on epsilon. From when I talk to x tau, I have managed to bring out this omega epsilon here squared. None of this discussion will matter to x, because whether I want to view x as a function of t or tau, it's up to me. And also it's not going to affect it here. It's only the derivative that has brought in these two. But now I have a function x of tau that I'm looking for. And really, I can now write x tau epsilon. Okay. And then for that x tau of epsilon, I can just use my regular expansion that I have done before, because this funny business of dependence on epsilon is gone. So the way I now go ahead is I will follow the exact same ansatz, but now in terms of x tau. So I will write x epsilon of tau, okay, is equal to phi naught of tau plus epsilon times phi 1 of tau plus the rest. And this, you could say I'm doing the same thing now, except, and you're right, at this level I'm doing the same thing, but in the end, when I pass back to the real time, then even this term here will depend on epsilon, because when I pass back, I will have to go from the tau time to the t time, and doing that will bring in this omega epsilon, which I'm hoping to get from this relationship. So I have achieved then the Lindstedt idea of grouping simply the solution in a different way. So I take the same expansion now, but apply to this equation. So the tricks have ended, no more tricks. I just brought this equation to a different form. And then again, I resort to the CR dependence of the solution on epsilon and just apply it to this one. And I will just do that expansion, okay? But I'm also expanding omega epsilon. So omega epsilon, the expansion of that is here. I had to square it, remember. So this is what I'm working on here. So when you have this sum and you have to square it, the first term will be 1, right? Then you have 2 times epsilon times omega 1, because look at here, what I have there, plus all high order terms. So I'm only just writing it out of leading order. So this is what this was omega epsilon squared. All right, let's keep going. X double prime. Well, just good old Taylor expansion. I'm expanding X as I did before. It's phi naught plus epsilon phi 1, and there's no funny business inside because I'm working with this time now, okay? And for all I know, that's just the regular Taylor expansion of the solution that I used before. This term is not problematic here. That's just, again, the same Taylor expansion here. And this is the nonlinear term right there, okay? Same procedure, I match equal powers of epsilon, and lo and behold, at order 1, what are the leading order powers? This one, that one, and nothing else. I recover the exact same ODE with the exact same solution. And you might think that, well, I'm just repeating history here. It's the same thing because the leading order solution is just that. It checks out the initial conditions, but bear in mind that that's not quite true, because now tau, when I go back in the end to the real time, I will be carrying this dependence here already at leading order. Okay, and that was a very insightful thing to do from Lindstedt. However, does it help us? I go to the second order, And I need to collect terms of order epsilon. There will be this one multiplying phi, not double prime, okay? That appears here because I put it on the other side. Then let's fish for other order epsilon terms. I'm going to have one here, epsilon times phi1. All right, that appears here as phi1. And I also had just simply, that was the leading order term. And I also had epsilon phi1 from here. So as far as the left-hand side of the resulting OD, it's the same as it always has been. It's the same linear OD without damping. But then there will be terms that I already know that depend on phi naught, and I will have two of those. As I've already said, there's one coming from here. Here, phi naught double prime, okay, times 2 omega 1. That gives me an order epsilon term. I put it on the other side of the equation with a negative sign. And then I also have this term here, okay, which I'm also putting on the other side with a negative sign. So that's why I'm getting these two terms here. And when I again use the identity that I was talking about here, this identity, when I say a cosine cube of something, then I can use the linearization formula. It's 1/4 times cosine 3t plus 3/4 times cosine t. I'm using the same here. So those will be two terms that I have distributed in two different ways. Let's see, this is cosine t, cosine 3t. And there was an amplitude multiplying the cosine t that was a naught, but there's also that went into these two. Sorry, that's why it's the a naught cube is there because a naught is there. And then I had this additional term minus 2 omega 1 phi naught double prime. Now phi naught is a naught times cosine tau. I need to take the double prime of that. That gives me minus a naught cosine tau. Okay. And it's also multiplied by minus 2 omega 1. So that turns into plus 2 omega 1 plus a naught times a naught, and that multiplies cosine omega t. I just want to give you an idea how this came about. And you could say, well, this may have seemed like a good idea, but I have the same problem. I have a linear oscillator being forced by something benign, but also being resonantly forced by this term. So don't I end up having the same problem of not being able to satisfy the periodic ansatz? And you're right. If this term is there, again, you have growth of solutions, and it seems like big ado for nothing. However, things are slightly different here. I don't have to accept that conclusion. If I'm looking desperately for a way out, I can say, all right, but can I actually make that term vanish? Because if that term vanishes for some reason, then the whole problem goes away and I get a periodic solution. Well, I could, right? The reason being is that now I have a bit of freedom here, because a naught is given, that's given by the initial condition, but omega 1 is a naught. Can I just tinker with omega 1? Well, I hope I should, because in fact, omega 1 was an unknown. I have no idea what omega 1 is. So in fact, I was hoping to get this omega 1 for the procedure. And now comes the conclusion that, wow, so I get precisely the first correct approximation order, first order approximation of the periodic solution, if omega is in fact such that for that choice of omega 1, this term cancels out. So I make this 0. And when I solve this for 0, it gives me an equation for omega 1 as a function of a naught, which makes sense because my initial amplitude level then will influence my first order correction to the linear frequency. So the nonlinear change in the frequency will depend on the amplitude order. Okay. So once again, formally, I would have growing solutions, except if I select this term to vanish, which will give me this equation for omega naught, 3/8 times a naught squared, then that eliminates the resonance. And there shouldn't be any resonance because I know that physically the beam is oscillating. It is then possible when I choose that omega 1 to suppress that. So this would be my solution in that case. This comes from the homogeneous part here. And that term is actually not there. So when I construct the particular solution, I only have to account for that, which I did here. So there's that term. So homogeneous, and there's the particular solution. I just plugged in everything here. And when I go back to the real time here, it's like pass from tau to t, then all of a sudden cosine tau becomes cosine omega t, cosine tau becomes cosine omega t, 3 tau becomes 3 omega t. And that omega I have started building, because now I have the first order correction to that up to order epsilon squared error. And when you actually plot this first order approximation, the dots are the numerical values. When you run the numerics, the ODE solver on the full nonlinear system, right? Not on the approximation, excuse my scrolling, but on this one, then you see that for epsilon values, which is not even tiny, it's just 0.1, but it's not 0.0001. This approximation is already very, very good. So this first order approximation, even for epsilon equals 0.1, just nails the solution very accurately, right? All right, so what's the advantage of this? You could say, well, I can solve the whole system numerically. I've just done it and it takes a split second. Why do all this work? Well, the reason why you do all this work is that all of a sudden you have a closed form, very accurate solution, which at least for a small epsilon is head on, and you no longer have to do any numerics to see the consequences. So now you cannot change the initial. You can ask what happens when I change the initial amplitude, what happens if I change epsilon, and you could have a gazillion other parameters in the equation, which I left out for simplicity, but they would also appear here. And this is the way you can make predictions. This is how you see qualitatively what parameter has what effect on the system. This is the type of thing that we try to get out of dynamical systems, even though the system is nonlinear. So this is not an exact solution, but it's a good enough solution to make these conclusions. Let me stop here. Just a couple of minutes still, but I went over time one of these days anyway, so it's a good place to stop. If you have any questions, I'll take them. And next time, which is next week, we'll get now started on analyzing things in the phase space, first building up our knowledge from equilibrium points and to more complicated objects to clear these up. So that's it for today. Are there any questions?
Yes, I've got a question.
Please.
So when you spoke about this Lindstedt trick of regrouping terms,
right.
I'm a bit puzzled that you said you don't exclusively allow for the frequency or the period to depend on epsilon, but also, I mean, in principle, general other dependence of the phi i's. And yeah, if we do that, then I don't really see how this expression is valid. How can we then say that any term is of order epsilon to some power? Because, for example, if we allow the dependence of the phi i's on epsilon to the minus I, then all phi i's would be of order 1. And so how's that
epsilon
then?
To the minus I, you said, right?
For example, it's just one example of how.
Right. So we do some smooth dependence there in epsilon, right? In the end, you're right. I could get away with the less. So I don't want to assume singular dependence on epsilon, right? Because that would then violate all sorts of things that I believe in. That we had theorems for. So as long as we say that all those phi naught i's have additional dependencies on epsilon that might come in at higher order, then I think I'm not violating anything. You're right in the sense that in the end that was not needed because let's just go here. In the end, after I made this change of coordinates, I just said at this point strategically that let's just assume that at this point I can get away with, in fact, no further dependence in the phi i's on epsilon. So you're right in the sense that I should have emphasized this, that you know, I try my luck. Maybe this time it works, right? And I don't have to allow for that. But even then, singular dependencies on epsilon are not allowed because that would violate the smoothness. At that point, I should have said, and you're right in pointing that out, that you know what, at this point, even though originally with this idea, I allowed for that, and in some cases that is probably even needed, I'm just going to say that all the epsilon dependence is here, okay? And that's what I ended up doing when I wrote that at this point, we're just going to use the usual Taylor expansion. this one. Thanks for pointing that out.
Thanks. Yeah.
Yeah. Anything else? Looks like we're done. Good. Then enjoy the rest of the week and see you next week. Bye.